Hi guys, Vince here. Today we're going to be taking an in-depth look at the new Bantam Tools desktop CNC milling machine. I'll show you how to use the software and how to set up simple parts, as well as some of the more advanced things like flips and soft jaws, and also some of the planned probing. I'll tell you some tips and tricks for feeds and speeds and how to make a machine like this work for you. Thank you guys for watching, and let's jump right in. I really enjoy using this machine, and it's my current go-to for small prototype aluminum projects. The Bantam team has been great with customer service, and they really stay on top of updating their software. Speaking of the software, it's pretty sophisticated and has this iPhone-like feel to it. I really enjoy the interface, and it should be very easy for beginners to pick up. For their first desktop mill, Bantam did really well. And it's going to sound funny, but one of my biggest gripes is that there aren't any handles or reliefs cut into the bottom of the frame to help while moving it. On the inside, one of the first things you'll notice is how much space there is. There's quite a bit of room for chips, and there's plenty of room to get your hands in there and change your tooling out. Plenty of room for fixtures and material. The work area is 7 inches by 9 inches by 3.5 inches, and that's pretty substantial for the size of the machine. It uses 20 millimeter rails for the X and the Y axis, and 16 millimeter rails for the Z. The spindle is an ER11 with a 10 to 28,000 RPM range, and it's belt driven by a 250 watt BLDC brushless motor. Let's take a quick look at the outside of the machine. This machine is beefy. It's a well-built combination of billet aluminum for the frame, a heavy gauge stainless steel for the body, and plastic side panels and door to round out the package. There is an external e-stop switch and a hidden magnetic safety switch for the front door. There are isolators, rubber isolators at each corner and one in the middle, which you can't see, to prevent unwanted vibrations from traveling to your table or desktop that you put it on. You can see a couple stepper motors, one right here. These are NEMA 17s, and I believe they're a double stack 1.5 amp, which is plenty of power, especially because the lead screws increase the torque quite a bit. It has a couple vents, one right here and one right here. And one thing I do want to point out is that the controller and power supply are housed outside of the machine, which really helps with dust contamination and stuff like that. You just don't have to worry about it, which is really nice. Also, the power plug is just a simple 3-prong plug. Then you have your on and off switch, and then your USB cord to tie into your computer. By now, some of you may have noticed that this isn't exactly 100% stock Bantam Tools mill. It originally comes with this T-slot table that's the same size as its work area. It has an integrated L bracket and toe clamps. And while I don't have anything against it, I really like the modularity of the Saunders Machine Works fixture tooling plate. Also, we were able to extend the work area, the fixture area, I should say, so that you could actually hold a piece as big as the machine could mill without a problem. This just lets you have more freedom and flexibility in your fixturing and what size parts you can do. Also, we decided to modify our fixture plate to accept the L bracket, and that way you can still use the probing routine, and that'll probe this corner and this corner, and it'll get you here's your origin point, which is pretty nice, especially when you're using non-conductive materials and you don't have to mill on the outside of it. So you just put this in here and then use the toe clamps will work as well. You just won't have as much adjustability. I'd also like to show you another accessory we've been working on for these fixture plates. These are 1/4 inch alignment pins, and they allow you to precisely locate the fixed side of your mod vise via these 2 bores. And as long as you installed your fixture plate and trammed it in well, then whenever you put this in with these pins, it should be aligned very, very, very close. If you've never used the Bantam Tools software, I would recommend heading over to the Support Center page on the Bantam Tools website. Here, you'll find step-by-step tutorials for just about everything. Click on the desktop link and they cover Getting Started, Fusion 3D workflows including design, programming, and CAM templates, PCB and SVG workflows including engraving. Last but not least is safety and maintenance. I want to share with you one feature that I found was very helpful. The milling software tracks spindle time and it will alert you when it's time to retension the drive belt with the included tool. Milling on a desktop machine is hard enough, so anytime the software can take over some of the responsibility, especially with maintenance alerts, it's very, very welcome. Pretty cool feature. When you first open up your Bantam Tools milling machine software, you'll want to navigate to the Home tab. Here, you'll see the Getting Started project section. If you click on one of those links, it'll bring you to the Bantam Tools website where you see all the tutorials for their projects. I highly recommend cutting the aluminum tool holder first, mainly because it's a simple project and they give you the material, and also it's a really good idea to have a place to put your wrenches and all your collets that you'll be using. They walk through step by step on how to go through your workflow, how to upload G-code, and how to probe the machine. They also show you a little bit of advanced features like the SVG support. It's not something I use too often, but it's really nice knowing that you don't have to open up Fusion or use your CAM software every time you want to put in something a little extra, something a little special. For this video, I started with the bottle opener project. This part is simple to make and has a classic shape. The tutorial walks you through step by step and instructs you to use tabs and double-sided sticky tape to complete the part. After reading all the way through the tutorial, I decided that we needed to kick it up a notch. I mean, Bree already calls me a hot rodder, so might as well hot rod it, right? So I downloaded the Fusion file and I started to modify the shape of the part to make it my own. The main goal was to show you guys this machine's capabilities while developing as many consistent and reliable proven cut recipes as I could at the same time. I also wanted to utilize the replaceable soft jaws for the Saunders Machine Works Mod Vise so that we could machine the part on both sides and minimize post-processing like sanding or filing. The center of the part was stepped down, and since hexagons are the bestagons, we extruded them out of the core. This created a stylish, very lightweight, and surprisingly strong bottle opener. My workflow may be a little bit different than most, so let's just run through that real quick. When you first start the machine, you'll want to home it, and then immediately after you'll want to go into the initial setup tab and install a tool. I'll usually use the 1/4" probe because it comes with the machine and it's easy to use because you don't have to rotate it to hit a flute when you probe X and Y. When you start the sequence, it will ask if you want to move the probing location to a different spot on the bed. I usually choose to probe off of the upper vise jaw. This allows for a much shorter tool stick out possible than trying to probe off of the bed. However, it also means that your stock placement will not be accurately simulated on the screen. You might get some collision warning pop-ups, but the 3D simulation does not affect G-code. After your tool is installed, you'll want to go to the Materials Setup tab, input your stock size and run a probing cycle. The simple XYZ corner routine works great on most setups. Now that we had everything set up, it was time to throw down some Toolpaths and prove out recipes I didn't have yet. I used proven cut facing and adaptive recipes to cut out the bulk of the material and finish the top. I then came in with a 4mm DATRON single flute and cleaned up all the 2D contours. This proved to be difficult due to how many high tool engagement areas there were. After that, we switched over to a 1/16 2 flute to pocket and finish contour the internal hexagons. Next, I used a few different tools to find the perfect chamfer and roundover strategy, but I won't show that because it's kind of boring. So pretty much that finished up side A, and we were ready to cut the soft jaws. This was the first time I've used soft jaws in the Saunders MachineWorks Mod Vise, and I was pleasantly surprised on how simple and easy they were to use. First, I machined a spot where I could actually put in a pin and use the boss probing routine in the plan routine to set up this soft jaw easily and accurately. I then cut out the pocket and the jaws for the part, pocket toolpath, bore, a wall contour, and a chamfer just to finish it off. After that, I just copied some of the toolpaths from op 1 and finished the back side of that first part. While I would have really liked to use Fusion Simulation to test out the strength and see where this part would buckle under stress, we're going to test it out the old-fashioned way. You guys ready? I'm a little scared. I mean, it's 10 grams. Looks good though. Let's do it. Perfect. Now most people would have stopped right there, but I really wanted to dial in the toolpaths on this part, and I didn't want to have to keep removing these soft jaws. So I just added another jaw, and I made a double station. Some of you might have been able to tell because there was a step in here. This matches the step on the floating side of the other mod vise. This setup lets me machine 2 parts at one time, so I have half the tool changes, twice the productivity. I really enjoyed using this double station because every time it completed a cycle, you had a finished part. There were actually 43 toolpaths per cycle. It helps to really separate your toolpaths based on what tool it is and create NC programs for each tool. This will help you keep everything organized and separated. Now let's take a look at the tools we used for the final toolpaths. We started off with a 1/4 inch probe to probe in the material and the soft jaw. We then used a 6mm DATRON single flute to do the roughing. After that, we put in the DATRON 12mm 2 flute. Next, we used a Lakeshore Carbide 1/8 inch 3 flute variable to do the contour passes. After that, we threw in a DATRON 3mm single flute for the 3D surfacing on the pry bar areas of the tool. We then used a 2mm DATRON external radius tool to put the fillet on the outside of the bottle opener. And then for the hexagons, we used a 2mm single flute tool to pocket and do the internal contours. Last but not least, we just used a plain old 1/8 inch 2 flute chamfer tool to make the part look perfect. With 7 tools and 43 separate toolpaths, it's easy to see how something like this would easily overwhelm most people. So let's go over it real quick. Like I said before, it's best to use NC programs to post your files, and the Bantam post processor is meant to only post one tool at a time. So whenever you post a program, just make sure you have the same tool number for all of the toolpaths in your NC program. With this many tools, there are a few tricks in the Bantam Tools software to help everything go a little bit smoother. Let's open up a couple files and I'll show you. Start off with a 6mm. Okay. And then let's put in a facing toolpath, 12mm. All right. Now the plan probing is where you're going to do your special probing. Remember that pin that I had on the soft jaw? This is where I'd use the Boss Center Point Advanced Probing Routine. And I really enjoy these probing routines. I wish they were in the material setup probing routines, but I'll take what I can get. So, say we got to probe the boss, and I'm just going to go through this. I'm not actually going to do it. All right, and let's say you probe it, and it tells you that your offset is 2 in the X and 2 in the Y. All right. Now, if you have multiple toolpaths with different tools, you're going to manually have to enter in that plan offset into the next toolpath. And that's pretty important. That's something you'll definitely want to double check, because I have entered in a couple numbers wrong, and it's definitely not fun when your machine's totally not where it's supposed to be and not doing what it's supposed to be doing. You can double check by looking here, the plan placement, and just making sure that on all the toolpaths that you're running that they match up. And see, that doesn't match up. So I'll make sure I hit enter. And now there you go, 2-2, 2-2. So what's cool about the software is I can choose to mill everything, all the toolpaths. And when it's done with one, it will pretty much do its own M6 tool change command and prompt you to put in the next tool for the next toolpath. And it'll just continue to go down the line. And let's say you've worked really hard, you have all your toolpaths dialed in, everything's perfect. Another really cool feature is you can go right here and actually save your plan file. And that'll save all your toolpaths, that'll save your offsets, everything. And then you can just reset up everything at a later time and then just re-upload that plan file and it's all there. Already all done. With so many toolpaths, it would be impossible to go through each one separately. So I'm going to post the recipes on Proven Cut. And now I'd just like to show you some things that I've learned along the way and that help in a project like this. So this is my first time posting toolpaths from multiple setups at the same time. And you'll see if you do that, you'll get a little warning. Pretty much different WCS settings have been selected, but because my setups use the same origin point, it hasn't been a problem. You can just click through that, make sure you simulate everything, and you're good to go. The next tip is for wall contours. I originally started off with a 4mm single flute, but it just wasn't giving me the smooth sidewall that I wanted. So I switched over to an 1/8 inch 3 flute from Lakeshore Carbide. And I'm pretty sure it's because of how much flute engagement I had along the wall because the cut was so deep that it just gave me a much smoother cut, which turned into a smoother finish. Plus, I really like those Lakeshore Endmills, but when cutting dry, you can't really use them in a pocket due to chip clearing. So I use those mostly for wall contouring and outside geometry stuff. It is very important to rest machine, especially on a part like this, because you have so many areas of high engagement. So the next tip, 3D contour like this, I probably didn't have to use a ball end mill, but I really liked the way that it gave me those tiny little lines on the finish, but it was nice and smooth. Sometimes using a patch surface will help on a toolpath like this. I think I used it on this side, but I didn't really have to on this side. Probably should have, because in the parts you'll actually see a tiny faint line right here. So if I do a patch surface, I can tell it just to run across without actually having to retract every time it comes over the pocket. It's a lot easier than messing with boundaries and all that kind of stuff. Chamfers. All right, these are the things that make any simple little part look and feel fantastic. You know, that professional finish, that nice clean edge break. And on a desktop machine like this, it can sometimes be a little hard to get a decent sized chamfer to look pretty good. So what I usually do is I'll break it up into steps. And then sometimes I'll make a spring pass at the end. I'll come down usually a 10 thou width, and then from there I'll just come down 5 thou at a time. Usually you do about a 20 thou chamfer. I believe I did 10 thou in these hexes, and I just did a single pass. It worked out pretty good. This was my first time using a external radius tool, and this is a tool from DATRON, a 2 flute 2mm radius. And pretty much I treated it like a chamfer tool, but I used a trace toolpath so it actually traced the front of this part on the prise section. For this, I also stepped it down. I believe I started with a 10 thou and then stepped it down 5 thou at a time and did a spring pass as well. Even with cutting dry, left a beautiful finish. I almost forgot. So I started off using a 16th 2 flute for these pockets, and that was fine, but there was one toolpath where I forgot to check an area and I broke it, and this is the last one I had. So then I swapped in a 2mm single flute. And this was nice because a single flute tool evacuates chips pretty well by itself when you're not using any kind of air blast or vacuum or chip fan. And that's another thing I want to talk about. So I did use a chip fan at one point, but due to the RPM that I was running this at, I believe 26,000, I didn't feel like it had the kind of balance that I wanted. So I ended up taking that off and I just ran these dry without any chip clearing because, you know, that's real world. I'm not going to go in there and stop the program every 5 minutes to vacuum it out. And there you go. Some good tips, good tricks, and definitely check out Proven Cut for all these recipes. Well, that's about it. I want to say thanks to everyone watching, and I hope you guys enjoyed this little project and presentation. I would like to give thanks to Bree and the Bantam team for letting us borrow this machine and really putting it through its paces. Thanks for watching, guys. Until next time. Peace.